Chance to shine.
Alright, I'm ready.
You're on right now, so
I'm on?
yes.
Okay. So today we're going to do optimization and related rates problems. Alright, that's good, that's good. So today we're going to do optimization and related rates problems, and I'm going to start out with the related rates problem. So a conical cup 3 inches across the top and 4 inches deep is full of water. The cup springs a leak at the bottom and loses water at a rate of 2 cubic inches per minute. How fast is the water level dropping at the instant when the water is exactly 3 inches deep? So they give us the volume equation right here, which is helpful. And then we want to put in everything we know. So a radius equals 1.5. The height of the water equals 3. And the full height equals 4. So we know the radius isn't changing. So we can put dr over dt equals 0. We know that water is leaving the cone at negative 2 cubic inches per minute. So you don't want to forget the negative because water is leaving. And then we don't know the rate at which the height is changing. So we put 0. Okay, so we put a question there. We only want one variable in our problem, so we have to set up a proportion to put radius in terms of height. So you can put r over h equals 1.5 over 4. Then you'll get radius equals 3/8 h. So we can just put everything into our equation that we have. V equals 1/3 pi 3/8 squared times our height again. So we just simplify that. Here. And then the fun part is taking the derivative. So you don't want to forget this dh over dt after you take the derivative. And then after you have your derivative, you can just plug in everything that you know. So you know uv over dt equals negative 2. And you know that your height here is d. And then dh over dt. And then all you have to do here is simplify. And what you should get is negative 0.503 inches.
Alright, so today we're going to be doing a optimization problem, and the problem is a farmer wants to construct a rectangular pig pen using 400 feet of fencing. The pen will be built next to an existing stone wall, so only 3 sides of fencing need to be constructed to enclose the pen. What dimensions should the farmer use to construct the pen with the largest possible area? So, to start out, we'll draw a picture here. So, here would be the stone wall that we don't need to do anything with. And on a rectangle, these 2 sides will be equal, so we'll call these x. And this side will be different, so we'll call this one y. Alright, so then to start this out, we need to create 2 equations. So we will first create the perimeter equation, and we have 400 feet of fencing, so 400 will be our perimeter, and that will equal 2x plus y. So there's 2 sides of x and 1 of y. And then the second equation will be the area equation, which will be area equals x times y. So to begin the problem, first we need to solve this first equation for y, which would become y equals 400 minus 2x. So now we need to substitute this equation into this one. So it would be area equals x times 400 minus 2x. And now we multiply this out. So then, to create the optimization problem, we need to find the derivative and set that equal to 0 to find the maximum. So, the derivative of this is after we set this equal to 0, solve this now here, so that becomes and then you get x equals 100. That's our first side length here. And then now, next we plug this value into here to find the other side length. So you get 400 equals 2 times 100 plus y. Then you just need to solve for y here to get your second side length. And you get y equals 200. So the dimensions here that you would need is 100 feet by 200 feet. And that will give you the most possible area using 400 feet of fencing.
Okay, I'm doing a related race problem. And the problem is a trough is being filled up with swill. It's 10 feet long and its cross section is an isosceles triangle that has a base of 2 feet and a height of 2 feet 6 inches, with the vertex at the bottom. Swill is being poured in at a rate of 5 cubic feet per minute. When the depth of the swill is 1 foot 3 inches, how fast is the swill level rising? So, we know that volume equals the area of base times height. Or we can simplify that to 1/2 dH lowercase h times the height of the entire thing. We also know that the swill is being poured in at a rate of 5 cubic feet per minute. So that means the volume dV is changing, dV over dt equals 5. We also know that the height of the trough is not changing, so dH over dt is equal to 0. What we do not know is how much the swill, or lowercase h, is rising. So we write dH over dt. That's what we're trying to find. So now we need to find b, so we can get this to a more simplified term. So we're trying to find b in terms of lowercase h. So we know that b over 2 equals to 8 lowercase h over 2.5. Alright, so then that simplified comes out to b equals 0.5 or 0.8 when it hits h. Now we can start plugging into the equation. We get v equals 1/2 0.8 h times h times the height of everything. And that simplifies to v equals 0.4 h squared times h. Because we know the height of the trough is 10 feet, we can plug 10 in for h, and we get v equals 4h squared. Then, so we can plug in these numbers, we need to find the derivative of this equation. We get dv equal to 8h times dh over dt. We start plugging in the numbers. dv over dt equals 5 equals 8. We know h equals 1.25 because the 1.3 inches simplifies to 1.25 feet. And then dh over dt, because that's what we were trying to find. So then we start simplifying. We get 5 is equal to 10 dh over dt. That simplifies to dh over dt is equal to 1/2, and we have our units.